Some nights the sky feels closer than it should. You lie still, and the dark above you seems to soften, and for a moment, just a moment, everything quiet becomes something worth staying inside of. If that feeling sounds familiar, you might like to stay here a while. There's no rush, no place you need to arrive. Only if it feels right, let yourself settle in. Let your breathing slow, and allow the next few hours to carry you gently somewhere you've never quite been before. Now, let's drift. There is something most people never stop to consider, even on the clearest nights, even when the sky is full and the stars are bright, and everything looks exactly the way it always has. What you are seeing when you look up at the night sky is not the present, not even close. The light arriving at your eyes, right now, that soft, quiet light you might barely notice, left its source long before you were born, long before your parents were born. Some of it left its source before humans existed at all. It has been traveling toward you at the fastest speed anything in the universe can move, and it is only just now arriving, only just now touching the surface of your eye. Researchers who study stellar distances often describe this in a way that quietly shifts something in how you understand the night. When you look at a familiar star, one of the bright ones near the horizon, or the faint ones overhead, you are not seeing that star as it is. You are seeing it as it was. You are looking into the past, across distances so vast that the numbers lose their meaning if you think about them too directly. The nearest star beyond our own sun, a small and dimly burning star called Proxima Centauri, is close by astronomical standards, and even its light takes a little over 4 years to reach us. 4 years of traveling through complete darkness, through the cold and the silence between things, before it arrives here, before it arrives at you. Further stars take hundreds of years, some take thousands. A few of the points of light you can see on a clear night tonight, the ones near the edge of visibility, the ones your eye keeps losing and finding again, sent their light before the printing press existed, before the first European explorers crossed the Atlantic, before entire civilizations rose and fell and were forgotten. It seems in a way that the night sky is not a single moment at all. It is a kind of layering, a soft gathering of different pasts, all arriving together, all arriving now, all reaching you at the same instant, even though they began their journeys at completely different points in time. Scientists sometimes describe the night sky as a time map, and there is something gently disorienting about that in the best possible way, because it means the sky you see tonight is not a fixed thing. It is not a ceiling. It is more like a depth, a quiet, uncountable depth, full of moments that are no longer happening, full of light from things that may have already changed beyond recognition. That star you're looking at, it may not look the same anymore. Not really. Stars change. They burn through what they have. They swell and shift and dim across timescales that make ordinary human time feel like a breath held and released. And somewhere out there, in the immense and patient darkness of the universe, stars are ending right now. We just haven't seen it yet. The light of their ending is still on its way to us, moving through the quiet between galaxies across a distance that takes longer to cross than our entire history of looking up. It will arrive someday, Thousands of years from now, perhaps some person standing outside on a clear night will watch a light they have known all their lives quietly disappear. And they won't know, not immediately, that the star itself ended long ago, that the ending happened in complete silence, in complete solitude, with no one watching. There is something about that thought that sits very gently in the chest. Not a sad thing exactly, more like a recognition. The kind you feel when you look at an old photograph, the sense that time moves in only one direction, but light somehow carries pieces of the past forward, carries them right into the present, into your eyes on an ordinary night without ceremony. Researchers who study the large-scale structure of the cosmos often point out that the universe is not a static place, even when it seems still. Stars are being born in distant regions of space, right now, collapsing out of cold clouds of gas and dust, taking their first unsteady steps toward ignition. And stars are dying, cooling, releasing everything they held back into the darkness. The universe is always mid-process, always somewhere in the middle of something. But when you look up, when you really look up on a night like this, none of that movement is visible. The stars appear fixed. They appear permanent. They appear from down here, like something you can count on. And for any single human life, that is essentially true. The stars you see tonight are the same stars your grandparents saw and their grandparents before them. The constellations that ancient people named the patterns they used to navigate and to mark the seasons, those same patterns still hold their shape in the sky above you now. But they are changing, slowly, imperceptibly, the way all things change when the scale of time stretches far enough. Scientists have been studying what happens when the light finally runs out, not just for individual stars, but for everything. There is a long and gradual arc to the universe, a trajectory researchers have traced forward through extraordinary spans of time, and what they find at the end of that arc is a quiet so complete it becomes something else entirely. That is where we are headed tonight. Not quickly, not all at once, but gently, unhurriedly, the way you follow a river downstream without needing to know exactly where it goes. The night sky above you right now is full of light that has been traveling for centuries, full of stars at every stage of their lives, young ones burning hot and blue, old ones swelling toward red, ancient ones fading toward white. All of it layered together in that deep and patient darkness. And there is something almost restful in that, if you let yourself feel it. The sense that everything is already underway, that the universe does not need anything from you tonight, that it is proceeding as it always has, at its own pace, without urgency. The stars that are ending tonight will take thousands of years to tell us, and somewhere in between all of that, on a small and quiet planet, someone is lying still in the dark and letting the oldest light in the known universe wash gently over them. Which means the universe, in some quiet and unhurried way, has always been on its way to you. There is more to all of this than a single night can hold. And the further we drift into it, the more the boundaries between one idea and the next begin to soften, the way things do when the mind begins to slow and the body finds its way toward rest. Somewhere in the universe right now, deep inside a cold cloud of gas. No one has named something is beginning. Part 2. How stars are born in the silence. Between things, there is a kind of darkness that is not empty. You would not know it to look at it. Between the stars, between the galaxies, between all the points of light that you can see, and the many more that you cannot, there are vast regions of space that appear from every human vantage point to be simply nothing. Cold, featureless, without movement or form. But researchers have found that this apparent emptiness is not what it seems. Scattered through the universe in regions so diffuse and so far from any source of warmth that temperatures drop to within a few degrees of the coldest possible point, there are enormous clouds of gas and dust that drift in near-perfect stillness. Scientists call them molecular clouds, and they can stretch across distances so immense that even light moving as fast as anything can move would take hundreds of years to cross from one edge to the other. They are not dramatic things. They do not glow. Most of them are invisible to ordinary sight. They just exist quietly in the spaces between everything else, patient in the way that only very large and very cold things can be patient. And inside them, almost imperceptibly, something is always beginning. It starts with a small disturbance, a ripple of gravity, perhaps a pressure wave from a distant explosion, or just the slow accumulation of mass in one part of the cloud, drawing in slightly more than another. Scientists suggest that even the passage of a spiral arm through a galaxy, the slow rotation of the entire galactic structure itself, can be enough to nudge a cloud into motion. The threshold is extraordinarily low. The universe, it seems, does not need much of an invitation to begin building something. What happens next unfolds across millions of years. The cloud begins to collapse inward. Not suddenly, not with any drama. More the way a very soft thing settles under its own weight, slowly finding the lowest available shape. Pockets of denser material form within it, pulling in more gas from the surrounding regions, growing denser still. Each pocket begins to rotate gradually, the way water begins to spiral as it drains, not because anything is pushing it, but because the physics of spinning and falling together tend naturally toward that shape. These rotating pockets compress further. Their interiors grow warmer. The heat has nowhere to go, so it stays and builds. And over a span of time, longer than the entire age of the Earth, a core forms dense hot and beginning very faintly to glow. Researchers who study the early stages of stellar formation sometimes describe this phase with a word that feels almost biological. They call it a protostar, a not quite yet star, a beginning that has not yet decided what it will become. The protostar continues to gather material from the cloud around it, pulling in streams of gas along a swirling disk that forms at its equator. It grows, it heats, and eventually, after perhaps another few 100,000 years of this slow accumulation, the temperature and pressure at its core reach a point that is in a very real sense a threshold. At around 10 million degrees, hydrogen atoms begin to fuse. Two hydrogen nuclei come together and form helium-releasing energy in the process. This is nuclear fusion, and it is not an explosion, so much as a release, a long, sustained, incredibly powerful breath outward that pushes back against the inward pull of gravity. The two forces meet, and for a moment, that will last millions or billions of years, they find a balance. The protostar becomes a star. Light pours outward in every direction. The remaining gas and dust in the surrounding cloud are blown away, and what was once an invisible pocket of cold collapse becomes, in the scheme of things, a new point of light in the universe. Scientists estimate that at the peak of cosmic star formation, a period that occurred roughly 10 billion years ago, when the universe was still young and full of raw material, new stars were forming across the observable universe at a rate many times higher than they are now. It was, in the language of astrophysics, a very different kind of sky, one we will never see because the light from that era has long since scattered and redshifted into wavelengths the human eye cannot detect. We know it happened not by seeing it directly, but by reading the evidence it left behind in the composition of old stars, in the structure of ancient galaxies, in the faint and pervasive glow that fills the universe even now. There is something quietly moving about that, if you allow yourself to sit with it. The most fertile period of star formation in the history of the cosmos is already over. The universe made most of its stars long before Earth existed, long before anything that would eventually become life had any chance to look up and wonder. Those stars burned and died and scattered their materials into space. And the planets and the oceans and the chemistry that eventually produced living things, all of it came from the aftermath of that ancient, invisible productivity. We are, in a very specific and scientifically grounded sense, the debris of something magnificent that happened a very long time ago. The elements in your body, the carbon, the oxygen, the nitrogen, the iron, none of them were made here. None of them were made anywhere near here. They were forged in the cores of stars that no longer exist, in fusion reactions that ran for millions of years before those stars swelled and burst and released everything they had built outward into the surrounding space. That material traveled through darkness and eventually fell together into new structures, new clouds, new protostars, new planets, new you. Researchers have traced this lineage with remarkable precision. The iron at the center of every red blood cell moving through your body right now was almost certainly formed in the dying moment of a massive star, in the final collapse and rebound of a stellar core that happened billions of years before the solar system existed. The calcium in your bones, the oxygen in each breath you take tonight, the water that makes up most of what you are, all of it has a history so long and so strange that it becomes difficult to think about directly. So you don't have to think about it directly. You can just let it be there, the way background things are there, the way you don't have to think about the air to breathe it. What's interesting is that new stars are still forming. Quieter now, less frequent, more scattered, but still happening. Deep in molecular clouds that exist even within our own galaxy, protostars are collapsing into being right now tonight, in regions so dusty and so remote that their light cannot reach us for millions of years. The universe has not stopped making things. It is simply making them more slowly, more selectively, with what remains. Scientists sometimes describe the current era of cosmic history as the stellar age, a period perhaps 10 trillion years long in total, during which stars exist in significant numbers. We are inside that era now. somewhere in the earlier middle of it, as best as researchers can tell, which means there are still stars to be born, and still stars to end, and still an enormous amount of quiet cosmic process left to unfold. But the arc is clear. The raw material available for star formation is not being replenished. The gas that forms stars is slowly being consumed or scattered, and what is left grows thinner over time. Each new generation of stars forms from what the previous generation left behind, and there is always a little less to work with than before. The universe is not running out of time in any way that would feel urgent. The scale is too vast for urgency, but it is very gradually approaching a kind of threshold, a point beyond which the conditions for stellar birth will become rarer, and then rarer still, and then one day, in a future so far from now, it exceeds imagination, will not occur again. That last star, the one this night is gently moving toward, will not be born in a blaze of drama. It will condense, as all stars do, slowly and quietly in a cold and patient cloud of gas. It will begin as a protostar. It will cross its threshold and begin to burn. It will not know it is the last. It will simply be a star, and it will burn for as long as it has to burn. There is something in that which feels in its own strange way like a kind of grace. The universe continuing to do what it has always done right up to the very edge of when it can do it no longer. And right now, somewhere between all of that, between the first star and the last one, between the beginning of the stellar age and its slow ending, a single planet is spinning in the dark, and on it, something living is breathing gently and letting its thoughts become softer and slower and further apart. The stars outside, whatever age they are, whatever distance they come from, are still arriving, still reaching. Think for a moment about what it means to hold something together. Not to force it, not to clamp it still, but to hold it gently continuously in a kind of living tension, the way you might cup water in both hands without spilling it. That image, imperfect as it is, comes closer to what a star actually is than most descriptions do. Because a star is not in the way we often imagine it, a fire. It is a balance. At every moment of its existence, a star is engaged in something that has no real equivalent in ordinary life, a continuous negotiation between two immense forces pulling in exactly opposite directions. Gravity, patient and relentless, pulls every atom in the star toward the center, and the energy released by nuclear fusion at that center pushes back outward in all directions with extraordinary force. These two forces are almost perfectly matched. Not exactly, not permanently, but closely enough and for long enough that from a distance the whole thing appears simply to glow. Scientists describe this state with a term that sounds almost peaceful. They call it hydrostatic equilibrium, a kind of pressure balance. The star neither collapses inward nor expands outward. It holds its shape. It maintains its brightness. It simply continues, year after year, century after century, millennium after millennium, doing the same thing it has always done. Our own sun has been in this state for approximately 4.5 billion years, and based on what researchers understand about the rate at which it is consuming its hydrogen, it has roughly the same amount of time remaining before that balance begins to shift. 4.5 billion years behind it. 4.5 billion years more or less still ahead. That is a number that dissolves meaning if you press on it too hard. So perhaps it is easier to simply feel the scale of it, the way you feel the scale of the ocean, not by measuring it, but by standing at its edge. The sun from where we are looks like a simple thing, a bright disk, a source of warmth, something that rises and sets on a rhythm you have trusted your entire life without thinking about it. But inside that brightness, at its very core, the temperature reaches approximately 15 million degrees. The pressure is so extreme that it exceeds anything that can be meaningfully replicated in a laboratory. And in those conditions, hydrogen nuclei, the simplest atoms in the universe, single protons stripped of everything else, come close enough to each other that the force binding atomic nuclei together can reach across the gap between them. They fuse. They become something new. And in the process, a small amount of mass is converted directly into energy. This is the relationship that physicists describe in one of the most quietly astonishing equations ever written. The idea that mass and energy are not different things, but different forms of the same thing, interchangeable under the right conditions. What a star does every second of every day is transform a small portion of its own mass into the light and heat that radiate outward. It is in a sense spending itself, slowly, carefully across an almost unimaginable span of time, but spending itself nonetheless. The sun converts something in the range of 4 million tons of its own mass into energy every single second. And yet, because the sun is so enormously massive, this rate of consumption will not significantly affect its size or brightness for billions of years. It is like a candle, the size of a continent, burning a thread of wax, the width of a hair. The flame barely notices. Researchers who model the internal structure of stars describe layers within the sun that have different characters, different behaviors, different relationships to the energy passing through them. At the very core, fusion reactions release energy in the form of high-energy light. But this light does not simply travel outward and escape. It enters a region so dense that it bounces and scatters and is absorbed and re-emitted over and over again, a slow, wandering journey that can take, according to some estimates, somewhere between 10,000 and 100,000 years before the energy finally reaches the outer layers and begins its 8-minute journey to Earth. That warmth on your skin on a summer afternoon, the light that grew the food you ate, the energy stored in every living thing on this planet. It all comes from processes that began deep inside the sun, tens of thousands of years ago, long before any written language existed, long before the first cities were built, before even the domestication of animals, and it has been traveling slowly toward the surface and then across the 93 million miles of space between the sun and the Earth to arrive here now today as something as ordinary as sunlight. There is something in that journey that the mind wants to follow somewhere. The idea that what feels immediate warmth, light, the simple fact of a bright day, has its origins so far back in time and so deep in a process so fundamental to the universe that by the time it reaches you, it has passed through more transformations than you could count. And yet, it arrives simply, without announcement, without any indication of what it has been through. Scientists note that the outer layer of the sun, the visible surface, the part that produces the light we see is actually its coolest region, around 5,500 degrees compared to the 15 million at the core. This creates a kind of structure, a gradient from extraordinary intensity at the center to something almost gentle at the edge, and it is that outer gentler zone that faces the world, that meets the planets, that reaches in its diluted and patient form all the way to us. There is an analogy in that, if you want one, though you don't have to look for it. Beyond the visible surface, the sun extends further still into a thin, superheated atmosphere called the corona, which stretches for millions of miles into space and reaches temperatures that strangely are far hotter than the surface below it. This is one of the genuinely unresolved puzzles in solar physics. Scientists are still working to understand why the corona is as hot as it is, why the temperature should rise again so far from the core after falling so dramatically in the outer layers. The current understanding involves magnetic fields and waves of energy moving through the solar atmosphere, but the full picture researchers acknowledge is still being assembled. The sun, in other words, is not fully understood. Even this closest star, even the one that every living thing on this planet depends upon it, still holds questions that no one has completely answered. And perhaps that is one of the more comforting things about science if you think about it from a certain angle. Not that everything is known, but that even the nearest, most studied, most essential things in the universe still have something in them that remains open, still have edges where certainty softens into careful wondering. Every star you have ever seen in your life, every point of light on a clear night, every cluster in a dark sky, every distant smear of brightness that might be a galaxy full of billions of them, is doing some version of this same thing, holding itself together, balancing inward and outward, converting a small portion of its own existence into light and sending that light outward in every direction into the dark. Most of it reaches nothing. Most of the light from most stars travels through space for billions of years and never touches anything at all. It simply continues moving through the emptiness at the speed of light, growing slightly more diffuse as it goes, never stopping, never absorbed, never arriving. And then occasionally, rarely, by the mathematics of the universe, a small beam of it finds a planet, finds an atmosphere, finds a surface, finds an eye. The fact that any of it reaches anything is, when you think about it that way, already improbable. The fact that it reaches something that can feel it and wonder about it and lie quietly in the dark and let the thought of it become soft and slow, that is something the universe spent a very long time arranging. And it does not need to be dramatic to be extraordinary. The balance inside a star is a quiet thing. It does not announce itself. It does not pulse or flare or call attention to what it is doing. It simply holds, steadily, for longer than anything else in the known universe holds anything. And out here in the dark, on this side of all that distance, something else is holding too. A body at rest, a mind beginning to loosen its grip on the day, a breath finding its own kind of equilibrium, not forced, not managed, just settling into what it naturally does when nothing is required of it. There are other ways a star can spend its light, other stages, other shapes the balance eventually takes as the hydrogen slowly thins and the negotiation between gravity and energy begins very gradually to shift. That shift is not an ending. Not yet. It is more like the beginning of a long and quiet change. The kind of change that takes so long to arrive that by the time it does, everything around it has already become something new. Most of existence is not extraordinary. That is not a complaint. It is in its own way one of the more reassuring things. Science has quietly confirmed that the universe, for the vast majority of its time, is not doing anything dramatic. It is simply continuing, holding steady, moving through long, unhurried stretches where the most significant thing happening is that nothing in particular is changing. Stars live this way too. Once a star has ignited, once it has crossed that threshold and begun fusing hydrogen into helium, in earnest, it enters what astronomers call the main sequence. This is not a dramatic place. It has no defining event, no climax, no moment of transformation. It is simply the long, stable, largely uneventful middle of a star's life. And for most stars, this middle lasts an almost incomprehensible length of time. For a star like our Sun, the main sequence spans roughly 10 billion years. For smaller, cooler stars, the dim red ones that burn through their fuel so slowly and so carefully that they seem almost reluctant to spend it, the main sequence can extend far longer. Researchers estimate that the smallest red dwarf stars may remain stable and largely unchanged for hundreds of billions of years. Some may burn quietly for trillions, long enough that if life were to form on a planet orbiting one of them, that life could theoretically have more time to develop and change than the current age of the universe multiplied many times over. Think about that softly, without trying to calculate it. Hundreds of billions of years of steady, patient light. A star that simply continues day after day in a universe that has meanwhile transformed itself beyond recognition, while the star itself remains essentially the same. There is something worth resting in there, if you let yourself. The main sequence is stable precisely because of the balance described before, the equilibrium between gravity and radiation pressure. But within that stability, there are still slow and subtle changes happening, visible only across timescales that no individual observer could ever perceive directly. The Sun, for instance, is slightly brighter now than it was when the solar system first formed. Not dramatically, not in any way that a person living at any given moment in history would notice. But over billions of years, the gradual accumulation of helium in the core changes the conditions of fusion in small ways, and the star adjusts. It brightens very slowly. It expands in tiny increments. None of this is abrupt. All of it is unhurried. Scientists who study stellar evolution sometimes describe the main sequence as a kind of long exhale. After the turbulent process of formation, all that collapse and heat and accumulation, the star finally settles into what it is, and then simply is that thing for as long as its fuel holds. The word evolution in this context can be a little misleading. For most of the main sequence, very little is evolving in any obvious sense. The star is not moving toward something. It is not preparing. It is not building toward a transformation it can sense coming. It is simply burning and balancing and emitting light, and doing so with an equanimity that no conscious being has ever quite managed to replicate. Which brings up something interesting about how we experience time and how differently the same span of time can feel depending on where you are inside it. For a star, 1,000,000 years is not a long time. The physical processes that govern stellar structure operate on scales that make human duration irrelevant as a unit of measurement. But for the living things on a planet orbiting that star, 1,000,000 years is more than enough time to transform beyond recognition, to change language, change form, change everything about what a life looks like. The same span of cosmic time contains, from different vantage points, almost no change at all and almost incomprehensible change simultaneously. Neuroscientists and cognitive researchers have found something loosely analogous in the way the human brain processes time. Not across millions of years, of course, but in the way that the same duration can feel entirely different depending on what fills it, or what the body is doing, or how alert the mind happens to be. A minute of acute anxiety can feel like an hour. A quiet evening that simply passes can feel in memory like it lasted longer than a busy week. The brain does not experience time as a uniform flow. It experiences it through the texture of what is happening inside it. During sleep, and in the slow approach to sleep, the drifting threshold between waking and rest, the brain's relationship to time becomes especially fluid. Researchers have observed that as the mind quiets, as the activity in certain regions begins to slow and soften, the tight sense of sequential time that characterizes waking life begins to loosen. Moments stop feeling ordered. The boundary between now and earlier in the evening or earlier in the week becomes less sharp. Things that happened recently can feel distant, and things remembered from long ago can feel close and clear. This is not confusion. It is the brain relaxing its grip on the structure it imposes on experience during waking hours, the constant effortful work of tracking where you are in time, what has happened, what is about to happen, what needs to happen next. In rest, that work becomes less urgent. And in the space where it softens, something else opens up, a looser, more associative kind of awareness that researchers sometimes describe as hypnagogic, the mind's own version of the long middle, not yet asleep, not quite awake, but holding steady in something softer than either. Stars in their main sequence may be the universe's version of that state. Not in transition, not building toward or recovering from. Simply present in a very long, very quiet now. There is an immense variety within the main sequence, even if the phase itself is stable. Stars are not all the same kind of thing. The most massive stars, the brilliant blue ones that burn so intensely they exhaust their fuel in mere millions of years, live their main sequence lives like something lit too brightly too fast. They are luminous beyond anything the imagination can hold. A single one of them can outshine entire clusters of smaller stars, and yet measured against the lifespan of a red dwarf, they are barely there. They flash through their main sequence and arrive at their ending before most stars have barely begun. Researchers sometimes describe this as a trade-off built into the structure of stars, mass against longevity. The more massive the star, the hotter its core, the faster its fusion, the shorter its life. A star 10 times the mass of the Sun may live only a few tens of millions of years. A star, a tenth of the Sun's mass, may live for trillions. The universe, it seems, is in no particular hurry to resolve this. It simply allows the full range, the brief blazing giants, and the slow patient dwarves to coexist, each burning in its own way, each occupying its place in the stellar distribution without reference to what any other star is doing. There are estimated to be somewhere in the range of 200 billion trillion stars in the observable universe. Some researchers place the number higher. The figures themselves resist imagination. They stop meaning anything specific and become more like weather, something vast and surrounding that you can sense without being able to hold it in detail. But within that number, the most common kind of star by far is the quiet kind, the small, cool red kind that burns slowly and carefully and lasts the longest. The universe is by population a place mostly full of patience. The brilliant stars, the ones most visible to us, the ones that figure in mythology and navigation and the poetry of looking up, are actually the minority. They stand out because of their intensity, not their number. The common stars are the dim ones, the ones requiring a telescope to see from any meaningful distance, the ones that burn so gently their light barely reaches neighboring solar systems. But they are there, billions upon billions of them, scattered through every galaxy, quietly continuing. On timescales that make human history feel like a single afternoon, they are doing almost nothing at all, and doing it steadily, faithfully, without interruption. There is a particular quality of existence in that. Not heroic, not tragic, not striving, just continuing, just being what they are in the conditions they are in, for as long as the conditions allow. Researchers who study what is sometimes called the psychology of rest, the science of recovery of genuine stillness, of what happens to a body and mind that are allowed to simply be without demand, have found that one of the most difficult things for many people is to resist the feeling that stillness must be earned, that rest requires justification, that continuing without visible progress or effort is somehow less than what existence should look like. But the universe does not seem to share that concern. It allows its stars billions of years of quiet continuance. It does not require them to justify their burning. It simply holds the conditions in which they can exist and lets them. And somewhere in the long middle of all those stellar lives, somewhere in the quiet billions of years of steady light, a small blue planet orbits one of them, its nights growing cool, its days warm and reliable. Everything alive on it calibrated to the rhythm of that one star's slow and patient burning. And on that planet tonight in the dark, something is letting go of the effort of the day. Something is finding its own version of the long exhale. The body does this naturally when it is allowed to. The breath slows, the muscles release. The busy work of tracking and managing and preparing all of that becomes gradually less insistent. Not gone, not silent, just further away than it was a few minutes ago. And the mind, given enough quiet and enough time, begins to do what the main sequence does. It holds, steadily, without urgency. In the long cosmic story being told tonight, the stars that have spent their main sequence lives are now approaching something new. Not an ending exactly, but a change in the quality of the balance. A shift in what holds and what begins very gently to let go. That shift happens slowly. It happens in ways that only become visible after a very long time. And it begins, as most things begin, not with a dramatic announcement, but with a quiet alteration in what is happening at the center of things. There is a kind of change that does not announce itself. It does not arrive with a shift in the weather, or a sound you notice, or a feeling that something is different when you wake up. It simply accumulates quietly in the background of things, and by the time it becomes visible, it has already been happening for a long time. This is how a star begins to let go. Not with a rupture, not with any sudden failure of what has held it steady for billions of years. The change begins, as so many changes do, at the very center, in a gradual shift in the composition of the core. For most of a star's main sequence, life that core has been converting hydrogen into helium through nuclear fusion, releasing energy in the process. But hydrogen, however vast, the supply is not inexhaustible, and as the millennia accumulate, the proportion of helium in the core slowly grows. Helium does not fuse under the same conditions that hydrogen does. It requires far more heat and pressure to begin its own fusion reactions, conditions that the core at this stage cannot yet produce. So the helium accumulates. It settles into the center, dense and inert, an island of stillness in what has otherwise been a continuous act of energy release. And the hydrogen fusion, unable to occur in the helium-rich core, migrates outward, continuing in a shell surrounding that core, burning through material that was previously stable. This is the beginning of what astronomers call the subgiant phase. From the outside, the star looks much as it always has. There is no visible signal that anything is shifting. But the internal structure is reorganizing, slowly responding to the new distribution of material and energy. The core, no longer producing fusion energy, begins to contract under gravity, growing hotter and denser as it does because the gravitational compression itself generates heat. And the outer layers of the star, responding to the increased energy output from the hydrogen-burning shell, begin to expand, very slowly, imperceptibly, in any single moment. But over millions of years, the expansion continues. The star grows. Its outer layers cool as they spread across a larger surface area. Its color shifts from the yellow-white of a middle-aged sun toward the orange and red of something larger and cooler. This is the transition into what scientists call a red giant, and it is one of the most profound transformations in the life of any star, not because it is violent, but because of its scale. A star that spent billions of years the size it was can expand in this phase to hundreds of times its original diameter. When our own sun reaches this stage in roughly 5 billion years, it will expand far enough to engulf the orbits of Mercury and Venus and possibly reach the current orbit of Earth. The details depend on models that carry their own uncertainties, and researchers continue to refine them. But the broad shape of what will happen is clear. The sun will become something enormous and dim and red, and the solar system that formed around it, with all its familiar distances and rhythms, will be remade entirely. 5 billion years is not a number you can feel. It is too large for feeling. But it is worth holding lightly, the way you hold a stone you have found, not gripping it, just letting its weight rest in your hand. What is interesting about the red giant phase is not its drama, though the scale is genuinely extraordinary, but its slowness. The expansion takes millions of years. There is no moment at which a planet in the system could observe a sudden change. Each day would be imperceptibly different from the one before. The warming would be gradual. The growing brightness of the sky would accumulate so slowly that no lifetime, however long, would contain enough of it to notice. And yet the change would be total. Scientists who study what happens to planetary systems during stellar evolution have found that the expanding outer layers of a red giant carry material outward gas and dust shedding from the star's surface, driven by radiation and stellar winds, enriching the surrounding space with elements that were produced in the nuclear reactions at the core. The star, in expanding, is also releasing. It is beginning very slowly the long process of returning what it has held back into the wider universe. Researchers note that stellar winds, the continuous outflow of charged particles from a star's surface, are already part of a star's existence throughout its main sequence life. The Sun produces a solar wind that streams outward past all the planets, filling a vast bubble of space called the heliosphere with charged particles and magnetic fields. In the red giant phase, these winds intensify dramatically. The star begins to lose mass at a much higher rate, shedding its outer layers into space over millions of years. There is something in the physiology of letting go that finds its parallel here if you are open to it. Not a forced parallel, just a noticing. The body, in its move towards sleep, undergoes its own quiet reorganization. Core temperature drops slightly. Researchers have found that a small reduction in body temperature is one of the physiological signals that initiates the transition into deep sleep. Blood flow shifts, redistributing toward the skin, where the warmth releases outward. Muscle tension accumulated through the day, without awareness, gradually softens. The jaw, the shoulders, the small muscles around the eyes, they release in a sequence that happens largely without instruction, responding to signals from the nervous system that the time for vigilance has passed. This process, the body's nightly redistribution, its quiet shedding of the held tension of waking, is not unlike what a star begins in its late stages. The core draws inward, growing more concentrated and dense. The outer layers expand and release. What was held tightly at the center becomes, over time, something more diffuse, more distributed, more returned to the surrounding space. Both processes are in their own domains a form of preparation. The body is preparing for the kind of deep rest in which repair happens, in which memory consolidates, in which the nervous system processes what the waking hours accumulated. The star is preparing for the next stage of its existence, one that will look entirely different from what came before. The physiological changes that accompany the descent into sleep involve more systems than most people consciously realize. The heart rate slows, breathing deepens and becomes more regular. The digestive system quiets. The immune system shifts into a more active mode, taking advantage of the reduced demands on the body's energy to carry out maintenance that waking life delays. Researchers have found that many of the body's most essential repair processes are timed to occur during sleep, not because the body becomes inactive, but because it becomes differently active. The resources that waking requires for attention, movement, and response are redirected toward tasks that cannot be done as efficiently while the person is alert and moving through the world. There is a word for this in biology, a recognition that rest is not the absence of activity, but a reallocation of it. The The body does not stop when it sleeps, it changes what it does. The same might be said of a star entering its late stages. It does not stop, it reorganizes. The energy that was once directed outward in the steady radiation of the main sequence begins to drive something different expansion, shedding a slow unwinding of what was held in place for so long. And the helium in the core, accumulating quietly over billions of years, waiting for the conditions that will allow it to finally participate eventually in stars massive enough it gets its moment. As the core continues to contract and heat, a threshold is reached. The temperature climbs high enough that helium nuclei can begin to fuse, producing carbon and oxygen. This event, called the helium flash in lower mass stars like the Sun, happens suddenly on astronomical timescales, releasing an enormous amount of energy in what amounts to a brief cosmic exhale. The star adjusts again. It finds a new, if temporary, equilibrium. A second stability, less long-lived than the first, built on the fusion of heavier fuel. It continues changed, but continuing. There are layers to a life if you look at it over long enough time. Not the layers you are aware of in any given moment, the tasks, the relationships, the daily textures of existence, but deeper ones. Layers that only become visible in retrospect when you can see from enough distance that something that felt like continuity was actually all along a series of slow transitions. One kind of stability giving way almost imperceptibly to another. The brain researchers have found is particularly good at constructing a sense of continuity across these transitions. It tends to remember the self as more consistent over time than it actually was. Memory smooths the edges. The person you were 10 years ago feels like a version of who you are now, even though the beliefs, the habits, the concerns, the physical body itself have all changed substantially. Psychologists sometimes describe this as the continuity illusion. Not a flaw, exactly, but a feature of how autobiographical memory works. The brain tells a story about its own past, in which the protagonist stays recognizable even when the evidence examined carefully suggests something more like a slow succession of different people, each inheriting the history of the one before. Stars do something similar in their way. From a distance, a star is a star, a point of light, steady, consistent, reliably there. The internal reorganizations, the phase transitions, the gradual accumulations that eventually produce profound change, none of that is visible in any ordinary observation. The star looks continuous, even as it is inside, always changing. And what changes in the end is the balance. The sun will expand. It will shed its outer layers in long, slow spirals of gas that drift outward into space and are illuminated by the hot remnant core left behind. The remnant will cool. It will become eventually something very quiet, something that holds the memory of what it was for billions of years, slowly fading, giving back its remaining warmth to the dark. But that is not yet. That is a long way from the present moment. Right now, there is still time. Still the long drift of things approaching their eventual change. Still a star and a planet and a night that is already carrying whoever is listening very gently toward its own quiet threshold. The breath has been slowing for a while now, perhaps, without you noticing. The thoughts, if there are any, are softer than they were. And somewhere in the space between one and the next, something is already beginning to release. Not everything ends the same way. That might seem obvious when you say it plainly, but there is something worth sitting within it, the idea that the universe, which operates according to the same physical laws everywhere, has still arranged for endings to come in many different forms. Quiet ones, gradual ones so slow they are barely distinguishable from continuance, and occasionally, in the right circumstances, ones of extraordinary brief intensity that scatter light across entire galaxies. What determines which ending a star receives is more than anything else mass. The mass a star is born with sets almost everything about its life: how hot it burns, how long it lasts, and crucially, how it concludes. Researchers who study stellar evolution have mapped these pathways in considerable detail, and what emerges from that mapping is something that feels less like a single story and more like a family of stories sharing the same essential themes but arriving at different places. Begin with the most common kind of ending, because it is also the quietest. Stars like the Sun and the many millions of smaller stars scattered through every galaxy will end not with any explosion, but with a slow and gradual release. After the red giant phase, after the outer layers have been shed into space in expanding shells of luminous gas, what remains is the core. Dense hot, no longer capable of sustaining fusion, but still radiating the heat it has accumulated over billions of years of compression. Astronomers call this remnant a white dwarf. It is not a large thing by stellar standards. A typical white dwarf has roughly the mass of the Sun, compressed into a volume approximately the size of Earth, a density so extreme that a single teaspoon of its material would weigh several tons. And yet, it is not collapsing. It is held up not by fusion, not by any ongoing energy release, but by a quantum mechanical property of electrons, a pressure that arises from the fundamental impossibility at the subatomic level of two electrons occupying exactly the same state in the same place at the same time. Scientists call this electron degeneracy pressure, and it is one of the stranger things in physics, a form of support that has nothing to do with temperature or energy, but with the intrinsic nature of the particles themselves. The white dwarf simply cannot be compressed further, not because of anything it is doing, but because of what it is. And so it cools, very slowly over timescales that dwarf even the current age of the universe. A white dwarf radiates its remaining heat outward into space, growing gradually dimmer, gradually cooler over billions upon billions of years. Researchers believe that no white dwarf in the current universe has had enough time to cool completely. The universe is simply not old enough yet. But in theory, given sufficient time, a white dwarf will eventually cool to the temperature of its surroundings and become what physicists have called a black dwarf, a cold, dark, inert remnant that neither glows nor collapses nor does anything in particular. It simply exists in the dark, holding together against the void. There are no black dwarfs yet, not anywhere in the observable universe. They require more time than the universe has so far provided. But they are coming slowly over time scales that make human civilization feel like a passing thought. There is something unexpectedly gentle in that image, the white dwarf cooling quietly, not ending in any dramatic sense, just becoming something colder and quieter, year by year, century by century, until it is indistinguishable from the dark around it. A kind of fading so gradual, it barely qualifies as an event. The endings available to more massive stars are different in almost every respect. A star with significantly more mass than the Sun, say 8 or more times as massive, does not quietly shed its outer layers and leave a cooling remnant behind. It runs through its fusion fuel much faster, and it fuses much heavier elements in the process. After hydrogen and helium, the core turns to carbon, then neon, then oxygen, then silicon. Each stage is shorter than the last, and each produces a slightly different kind of energy, a slightly different equilibrium. The silicon burning phase, the final stage before the core reaches iron, lasts only a matter of days. Iron is where it stops. Iron fusion does not release energy, it absorbs it. A core of iron in the heart of a massive star is a dead end, and the star arrives there suddenly. With no more energy release to push back against gravity, the iron core collapses in a fraction of a second. The collapse is so rapid, the density so extreme, that the core rebounds, and the energy of that rebound drives a shock wave outward through the star's outer layers at a significant fraction of the speed of light. The result is a supernova, an event so luminous it can briefly outshine the entire galaxy containing it. But even here, the word explosion slightly misrepresents what is happening. Astrophysicists who model supernovae describe the process with a precision that tends to strip away any drama and replace it with something more interesting, a cascade of physics, each step following from the one before, each governed by forces and principles that operate the same way everywhere in the universe. The violence is real, but it is not random. It is structured, determined, the inevitable consequence of the particular arrangement of mass and energy that the star spent its whole life building. What remains after a supernova depends again on mass. The remnant core of a supernova, if it falls within a certain range of mass, becomes a neutron star. Neutron stars are among the most extreme objects in the known universe. Their density exceeds even that of a white dwarf by many orders of magnitude. A neutron star packs roughly 1.5 times the mass of the Sun into a sphere only about 20 kilometers across. The gravitational field at its surface is so intense that a person standing there, an impossible scenario, but a useful thought experiment, would weigh roughly 100 billion times what they weigh on Earth. Neutron stars often spin rapidly, emitting beams of radiation from their magnetic poles that sweep through space like lighthouse beams. When these beams happen to point toward Earth, we detect them as precise, rapid pulses, so regular that when astronomers first observed them in the 1960s, some researchers briefly entertained the idea that they might be signals of an artificial origin. They are not. They are simply physics operating with its characteristic indifference to human expectation. And then there are the stellar remnants of the most massive stars, of all those so large that even the quantum pressure of neutrons cannot hold them against gravitational collapse. These become what physics calls black holes, not empty space, but regions of such extreme space-time curvature that nothing, not matter, not light, not information in any form can escape from inside a certain boundary. The physics at the center of a black hole exceeds what current theory can describe. It is one of the places where the most successful frameworks scientists have for understanding the universe reach their limits and go quiet. There is something appropriate about that, perhaps, that the most extreme endings are also the ones most resistant to complete description. But return for a moment to the white dwarf, to the quiet ending. Because for the purposes of this particular night, this particular hour, that is the ending most relevant to the story being told, a star like the sun, shedding its outer layers in beautiful expanding shells of gas, leaving behind a small, dense, cooling remnant that asks nothing more of the universe than to be allowed to exist and slowly release what it holds. Astronomers have photographed these expanding shells. They are among the most visually striking objects in the sky, luminous rings and spheres of ionized gas, glowing in colors determined by their chemical composition, lit from within by the hot white dwarf at their center. Scientists call them planetary nebulae, a name that reflects an early misidentification, rather than any actual connection to planets. They look through a telescope like pale and luminous disks, soft at their edges, layered with structure, neither entirely symmetrical nor entirely random. They are, in a real sense, what a star looks like from the outside when it releases what it has spent its whole life building. The gases expanding outward from a planetary nebula will eventually disperse into the surrounding interstellar medium, becoming part of the diffuse clouds of material that drift through the galaxy. Some of that material may, over millions of years, become part of new molecular clouds. Some of those clouds may collapse into new protostars, and from those protostars, eventually new worlds may form, carrying within them the atoms that were once at the heart of something that burned for billions of years and quietly, patiently let them go. The human body processes endings in ways that neuroscience has only recently begun to map with any precision. When something comes to a close, a relationship, a chapter of life, even just the end of a long day, the brain does not simply register absence. It processes. It consolidates. It moves certain things from active attention into something more like storage. Researchers have found that the sleeping brain is particularly active in this kind of consolidation, taking the emotional residue of what the waking day carried, and during the slow cycling of sleep stages, finding places for it that require less effort to hold. What was pressing becomes settled. What felt unresolved has by morning sometimes simply softened, not solved necessarily, but rearranged into something less sharp. Psychologists note that this is one of sleep's less celebrated but genuinely important functions. Not only rest, not only physical repair, but emotional reprocessing, the quiet, unconscious work of finding equilibrium with what the day contained. Stars do a version of this across time scales that make the comparison almost absurd, but the shape is similar. What was held under enormous pressure for an almost incomprehensible duration eventually finds its way outward. It disperses. It becomes part of something else. And the core of what remains continues cooler and quieter than before, but continuing. The endings of stars are not in most cases dramatic. They are patient. They are gradual. They are, in the largest sense, simply the universe continuing to do what it has always done, rearranging what it contains, moving matter and energy from one form into another, carrying forward the legacy of everything that came before. And in the long arc of all those endings, something accumulates in the darkness between the galaxies, something made of everything that has been released, something that is neither the stars themselves nor empty space, but the residue of billions of years of quiet, stellar living. It is out there right now, drifting, and in much the same way that the body moves towards sleep, not by stopping, but by shifting, redistributing, releasing, allowing certain things to settle, the universe continues, even after each individual light goes out to carry everything forward. The dark between the stars is not absence. It is everything those stars have ever given back. There is a particular feeling that comes with the late hours of something. Not sadness exactly, not urgency. Something quieter than either the sense of a pace that has changed, a rhythm that has slowed from what it once was. The way a party feels in its final hour. The way a season feels in its last week. Not over, still present, but measurably different from what it was at its fullest. The universe has that feeling now if you know where to look for it. Not in any single place, not in any obvious signal, but in a broad, measurable, well-documented trend that cosmologists have spent decades piecing together from observations across billions of light-years of space, the gradual, undeniable slowing of the universe's star-making activity. At its peak, roughly 10 billion years ago, the universe was forming stars at a rate approximately 10 times higher than it is today. Some estimates place the difference even higher. The raw material was more abundant, the conditions more favorable, and new galaxies were still assembling themselves from collisions and mergers that funneled enormous quantities of gas into their centers, triggering vast waves of star formation that lit the early universe with an intensity it has never quite recovered. Astronomers call this era cosmic noon, not because it was literally the middle of time. The universe had already been expanding for several billion years by then, but because it was the period of maximum stellar productivity, the peak of the universe's creative output, the moment when new light was being generated at the highest rate the cosmos has ever managed. And since then, steadily, the rate has declined. This is not a dramatic decline measured in any short span. On the scale of a human lifetime, or even on the scale of recorded history, the universe's current rate of star formation would appear entirely stable. Nothing is visibly winding down. The night sky tonight looks to ordinary observation exactly as full and as permanent as it did 10,000 years ago. But in the data, in the careful accounting of how many new stars are forming per year across the observable universe, the trend is unmistakable. The universe is making stars more slowly than it used to, and researchers believe this trend will continue. The reason is relatively straightforward, even if the details are complex. Stars form from gas. The gas that is most available for star formation exists in specific regions of galaxies, dense molecular clouds, in flowing streams of material regions where pressure and gravity happen to cooperate. But star formation is not a perfectly efficient process. A great deal of the gas involved in forming stars never actually ends up in the star. Some is blown away by the radiation and winds of the newly formed stars themselves. Some is heated by supernovae to temperatures that prevent it from collapsing back into new stars for millions of years. Some escapes the galaxy, entirely drifting out into the vast space between galaxies, where it becomes essentially inaccessible for future star formation, and the supply is not being meaningfully replenished. Galaxies in the early universe were actively accreting fresh gas, drawing in material from the cosmic web, the vast filamentary structure of gas and dark matter that connects galaxies across large-scale cosmic distances. This inflow sustained the high rates of star formation during cosmic noon. But as the universe has aged and expanded, these inflows have diminished. The cosmic web has become more diffuse, the reservoirs are depleting, and the rate at which new material becomes available for star formation has steadily decreased. Researchers who model galactic evolution describe current galaxies as living on what they sometimes call a closed box, a system that is mostly recycling what it already contains, rather than drawing in significant new input. Stars form, enrich the interstellar medium with heavier elements when they die, and the next generation forms from that enriched material. But with each cycle, a little more is locked up in stellar remnants, white dwarfs, neutron stars that contribute nothing to future star formation. The available gas fraction shrinks slowly with every generation. This is happening in the Milky Way right now. Our galaxy is forming new stars at a relatively modest rate, perhaps a few solar masses worth of new stellar material per year. A fraction of what it once managed, and a fraction of what some other younger galaxies are still achieving. The Milky Way is not dying. It is simply aging in the way that large systems age, maintaining most of its function, still doing recognizable versions of what it always did, but at a pace and with an energy that is quieter than its earlier chapters. There is a concept in the study of aging systems, biological ones in particular, that researchers sometimes describe as a gradual shift from growth to maintenance. Young organisms, young ecosystems, young galaxies invest their resources primarily in expansion, in building new structures, new connections, new capacity. As they mature, the balance shifts. More energy goes toward maintaining what already exists, toward repair, toward sustaining the complex arrangements that have already been assembled rather than building new ones from scratch. The universe seems to be following something like that arc. The great burst of creation, the extraordinary productivity of cosmic noon has given way to something more measured. The universe is tending to what it has already made. It is sustaining the stars that exist. It is processing the material that previous generations of stars released. It is, in the broadest sense, in a maintenance phase, still generative, still capable of producing new things, but doing so with the care and selectivity of something that knows its resources are not unlimited. And in this phase, the things that exist feel, if you let yourself sense it, a little more precious. Not because they are disappearing, not quickly, not on any scale that matters in a human life, but because the background rate of creation has slowed enough that what is here now is, in some diffuse cosmic sense, more rare than what was here before. The stars you see tonight are not replaceable at the rate they once were. That is worth holding for a moment. Not with grief, just with attention. The quiet way you might hold the last good hour of an evening that has been genuinely fine. Astronomers studying galaxy evolution have identified a class of galaxies sometimes called red and dead, large elliptical galaxies that have used up most of their available gas and largely ceased forming new stars, existing now as collections of old, cool reddish stars that are slowly aging together. They are not gone. They are still there, still luminous, in a subdued way, still full of billions of stars going about their individual stellar lives. But the generative phase, the period of rapid expansion and star birth, is over for them. They have settled into something like old age. Vast, quiet, mostly stable. The Milky Way is not yet in that phase. It still has enough gas to form new stars for billions of years. But it is relative to its own past, and relative to the universe's overall trajectory, closer to that settled state than it is to the wild productivity of cosmic noon. And here is what is easy to miss in this picture. The slowing is not failure. It is not decay in any negative sense. It is simply what happens when a system has done a great deal of work over a long time. The resources become more distributed, more dilute, more widely spread. The rate of production decreases. But the products of all that earlier work, the stars already formed, the planets already assembled, the complex chemistry already underway on countless worlds, all of that continues. All of that is already out there, already unfolding, already in the middle of whatever it is doing. The slowing of star formation does not undo anything that has already been made. There is something the mind does in the later hours of a day that is worth noticing, a kind of natural deceleration that happens not because you decide to slow down, but because the systems that were running at full capacity during the morning gradually shift their operating mode. Alertness narrows. Attention becomes less broad, less grasping. The ability to hold many things at once begins to simplify. Researchers who study circadian rhythms and cognitive performance across the day describe this as a predictable biological pattern, the brain and body moving through cycles of activity and rest that are built into the fundamental timing systems of almost every living thing on Earth. These timing systems are ancient. They evolved long before humans, long before mammals, in organisms that were responding to the basic rhythm of a planet rotating under a star, the cycle of light and dark that the sun's position imposed on every living thing that ever existed on this world. The very structure of when the body slows and when it rests is a legacy of stellar physics in the most direct possible way. The rhythm of the sun, the particular star at the center of this particular solar system, is written into biology itself, into the genes and the cellular machinery of every organism that lives beneath its light. So when the body begins to slow in the late hours, it is not failing. It is responding to the oldest signal. There is the signal built into it by billions of years of life on a planet that turns and darkens and rests. The universe slowing in its star formation is doing something that feels similar in spirit, not ending, not declining toward nothing, but transitioning from one kind of activity to another, from creation to tending, from expansion to maintenance, following an arc that once you see it, feels less like loss and more like the natural shape of very long and very productive lives. And the stars that exist right now, this generation of stars, the one currently burning across every galaxy in the observable universe, the one our own sun belongs to, are among the last of the abundant ones, the ones that formed when there was still plenty of material, the ones born before the gas ran too thin. That does not make them any dimmer tonight. If anything, it makes the light of them feel slightly warmer, slightly more worth noticing. The dark outside, wherever you are right now, is full of that light, crossing the distances it has always crossed, arriving the way it always arrives, touching the surface of things that are resting and breathing, and slowly releasing the effort of the day. The universe, too, is in its own long exhale, and both in their own time and their own scale are doing exactly what they are supposed to do. There is more to follow still, further into the dark, further into the long arc of what happens when the light begins very gradually to thin, and what is left in the spaces that the stars once filled is stranger and quieter than anything the imagination easily holds. But for now, just this: the light that is still arriving, the breath that is still slowing, the night that is still unhurriedly deepening. Somewhere in your body right now, something very old is happening. Not metaphorically, not as a way of speaking. Literally, in the actual material of you, in the atoms that make up the cells that carry out every process, keeping you alive and resting in this moment, something is occurring that began long before the Earth existed, long before the Sun existed. In the cores of stars that finished their lives billions of years ago and were never known by anyone. The iron in your blood is the most direct example, and it is worth staying with for a moment. Every red blood cell moving through your body contains a protein called hemoglobin, and at the center of each hemoglobin molecule sits a single iron atom. That iron atom is responsible for binding oxygen in the lungs and releasing it to tissues throughout the body, a transaction so fundamental, so continuously repeated, that it defines the basic chemistry of your survival. Without iron in that specific role, in that specific location, the system of oxygenating a body simply does not work. And that iron, each individual atom of it, was forged inside a star. Not our Sun. The Sun does not produce iron through its current fusion processes. Iron is a heavy element, and it requires either the extreme conditions at the core of a dying massive star or the violent collision of neutron stars to produce it in significant quantities. Researchers who study stellar nucleosynthesis, the process by which stars build heavier elements through nuclear fusion, have traced the origin of iron to these specific, relatively rare events: a massive star burning through its final fuel stages, a neutron-star merger sending ripples through space-time while simultaneously seeding the surrounding space with newly forged heavy elements. The iron in your blood then has a biography that is extraordinary in its length and its strangeness. It was made in the death of something enormous. It was scattered into space. It drifted. Over millions of years, it became part of a molecular cloud. That cloud collapsed slowly into a new generation of stars and planets. One of those planets, this one, accumulated iron across its formation, and over billions of years of geological and biological evolution, life on that planet developed the chemistry to use it. You inherited iron from a star that no longer exists. The calcium in your bones follows a similar path produced in stellar nucleosynthesis during the late stages of massive star evolution. The oxygen in the water that makes up most of what you are was created in the same stellar processes. The carbon that forms the backbone of every organic molecule in your body, every cell membrane, every strand of genetic material, every protein folded into its precise working shape, was built by helium fusion in the cores of stars during their red giant phases. Researchers sometimes summarize this with a phrase that is so compressed it can almost lose its meaning. Through familiarity, we are made of stardust. But the scientific reality behind that phrase is considerably more specific and considerably stranger than the poetic version. It is not simply that the universe is old, or that everything is connected in some vague cosmic sense. It is that the actual atoms constituting your body were processed through the nuclear reactions of actual stars, were scattered by actual stellar deaths, and traveled through actual interstellar space before arriving through a chain of events that took billions of years at the arrangement that is currently lying still and breathing slowly in the dark. The specificity of it is what makes it remarkable. Not that we are part of the universe in some general way, everything is trivially, but that the universe, in making us, used particular stars in particular places at particular times, and those stars went through their complete lives and died, and the products of those deaths traveled specific distances and underwent specific transformations before arriving here. Your existence required those specific stellar deaths, and the universe has a way of carrying its history forward in the composition of things. Astronomers can read this history in the spectral lines of starlight, the characteristic patterns of absorption and emission that different elements produce when light passes through them. Every star's light carries a fingerprint, a precise record of what it is made of, and from that fingerprint, researchers can determine not only the star's composition, but something of its history, whether it formed early in the universe or later, whether it was born in a region rich in heavy elements or one still dominated by the original hydrogen and helium of the Big Bang. The stars that formed earliest before the universe had time to produce significant quantities of heavier elements are sometimes called metal poor, using the astronomer's convention of calling any element heavier than helium a metal. These ancient stars are made almost entirely of the original material. They have almost none of the iron, carbon, silicon, or oxygen that later generations carry. They are, in a sense, the least processed things in the universe, the closest existing thing to the original state of matter after the Big Bang. And then there are stars, like the Sun, third generation or so, formed from material that has already been through multiple cycles of stellar birth and death, enriched by the nucleosynthesis of many previous stellar generations. The Sun's composition reflects a long history of earlier stars living, dying, and returning their materials to space. It is, in the language of stellar astronomy, a reasonably metal-rich star, which means that the planet that formed around it and the life that eventually emerged on that planet had access to a wide palette of heavy elements that the earliest stars never provided. The universe has been building toward greater chemical complexity across its entire history. Each generation of stars enriches the interstellar medium with heavier elements than the previous generation left behind. Each cycle of formation, fusion, and dispersal produces a slightly more chemically diverse universe. Life, as researchers understand it, requires this complexity. It requires carbon, oxygen, nitrogen, phosphorus, sulfur, iron, and dozens of other elements in precise combinations that simply did not exist in sufficient quantities in the early universe. So life, in a very real sense, had to wait. It had to wait for enough stellar generations to pass, enough deaths, enough dispersal, enough mixing of the interstellar medium, enough time for the galaxy to accumulate the chemical palette that living systems require. We are not just made of stars. We are made possible by the death of many generations of stars. There is a quality to that idea that changes very slightly how the body feels against whatever it is resting on right now. The weight of it, the warmth of it, the particular atoms of skin and muscle and bone, each with their long and improbable biography, each having passed through fire and traveled through darkness and waited through unimaginable spans of time to end up here in this specific arrangement, in this specific moment. It is not a dramatic thought. It does not need to be held with any particular feeling. It can simply sit there in the background of things the way very old and very true things tend to sit. The body is extraordinarily good at carrying its history without drawing attention to it. The heart beats without asking for awareness. The liver filters without announcing itself. The nervous system processes an extraordinary volume of sensory information and passes only a tiny fraction of it into conscious experience. Researchers who study the body's unconscious processes have found that the vast majority of what the biology is doing at any given moment is entirely below the threshold of awareness, not hidden exactly, but simply not offered up unless specifically sought. The sleeping body continues this in an especially thorough way. During sleep, the biology does not slow down, it redirects. The brain cycles through distinct stages, each characterized by different patterns of electrical activity. During the deep stages, growth hormone is released in its highest concentrations of the day, triggering cellular repair and physical restoration. During the lighter stages, the brain engages in memory consolidation, not passively, but actively replaying and reorganizing the experiences of the day, deciding what to retain and what to release. The immune system uses the reduced energy demands of sleep to carry out surveillance and maintenance functions that cannot be efficiently done during waking hours. All of this happens without your participation. The same atoms that were forged in stars, that traveled through interstellar space, that were incorporated into living biology billions of years in the making, those atoms are now in the dark and quiet of this night, continuing their long work, building, repairing, processing, carrying forward the legacy of everything that made them. And the extraordinary thing about legacy, whether in the universe or in a single living body, is how it continues without requiring the original source to remain. The stars that made you are gone. Most of them have been gone far longer than the Earth has existed. Their light, if it ever reached this part of space, has long since passed and continued outward, thinning into silence. But what they made is still here, still working, still in a sense that is completely literal and not at all abstract, still doing the work of the universe, just in a different form than a burning ball of fusing hydrogen. The carbon in you is doing chemistry. The iron in you is carrying oxygen. The calcium in you is holding structure. The nitrogen in you is encoding information. The star is gone, but its work is not finished. That thought has a particular quality to it in the late hours of a night. The sense that what continues after a source is gone can still be meaningful, still active, still in its own way, doing something worth doing. And perhaps that extends further than biology. Perhaps it extends into the broader pattern of what the universe does, how it carries its history forward, not as preserved relics, but as living processes. How the past does not so much end as transform into the ongoing present. The stellar material drifting through the galaxy right now, the gas and dust enriched by generations of stellar death, the streams of heavy elements moving slowly through the interstellar medium, all of it is in a very real sense a form of memory, not conscious memory, not stored in any structure that resembles how a brain holds experience, but a physical record carried in the composition of things, of every star that has ever lived and died and given back. The universe remembers its stars by continuing to carry what they made. And tonight, in one very small part of the universe, some of what they made is resting, is quiet, is doing in its own slow and biological way exactly what it needs to do. The breath finds its own pace. The body settles into whatever it is settling into. And the atoms, patient and unhurried, continue their ancient and ongoing work as they always have, as they will, for longer than can be imagined. Somewhere further along the arc of time, the last of these stellar legacies will also come to rest. The last white dwarf cooling. The last neutron star spinning down. The last organized structure of the kind that existed when stars were plentiful, slowly giving way to something quieter still. That is where the story is going. Into the long and extraordinary silence that follows. Try for a moment to imagine a number that has no useful comparison. Not a large number in the way that 1,000,000 or 1,000,000,000 is large. Those numbers still have things to stand next to. 1,000,000 seconds is about 11.5 days. 1,000,000,000 seconds is roughly 32 years. These are large, but they are still humanly imaginable, still anchored to something a life can contain. The number 100 trillion is different. 100 trillion years. Written as a numeral, it is a 1 followed by 14 zeros. Set against the current age of the universe, approximately 13.8 billion years, it is roughly 7,000 times longer than everything that has happened so far. Every star ever observed, every galaxy ever mapped, every moment of cosmic history, from the first light to this one, represents less than a single fraction of 1% of the span of time being described. And yet that is when, according to the best current models of stellar physics, the last ordinary star will exhaust its fuel. Researchers who study the long-term future of the universe, a field sometimes called physical eschatology, have traced the evolution of stellar populations forward through these extraordinary spans of time, and what they find is not a dramatic conclusion, but a gradual thinning. Stars will not go out all at once. They will go out one by one, spread across a duration so vast that the interval between one stellar death and the next will itself be longer than the current age of the universe many times over. It will not feel from any conceivable vantage point like an event. It will feel, if anything can feel at all, by then like the slow and irresistible settling of something very large into stillness. The last stars to burn will almost certainly be the smallest ones. The red dwarfs, those dim, cool, patient stars that burn their hydrogen so slowly and so carefully, will outlast everything else. Stars with masses around 8% of the Sun's mass burn at such low temperatures that their fusion reactions proceed at an almost geological pace. Their lifespans extend into the trillions of years, and they have one additional property that makes them especially long-lived. Unlike larger stars, which develop distinct internal zones where convection and radiation each dominate different regions, the smallest red dwarfs are thought to be fully convective throughout, meaning the gas inside them circulates all the way from the core to the surface and back. This constant mixing prevents the accumulation of helium in the core that shortens the lives of more massive stars. The red dwarf can access and burn nearly all of its hydrogen fuel, not just the fraction near its center. It is, in a sense, a more efficient machine than the Sun, quieter, cooler, and very nearly complete in its use of what it has. So the last star will be a red dwarf, small, dim, invisible to the naked eye at any significant distance, burning with a deep red glow that a human eye in current evolutionary form would barely register as light, and it will burn alone. By the time the last star approaches its end, the universe will be unimaginably different from what it is tonight. The expansion of space, already detectable in the recession of distant galaxies, will have continued for so long that virtually every other galaxy currently observable will have receded beyond any causal contact with the Milky Way. The cosmic horizon will have closed around our local group of galaxies. Everything beyond that horizon will be, in every physically meaningful sense, gone, not destroyed, but moved so far by the expansion of space that no signal, no light, no information of any kind can ever travel between here and there again. The universe will have become, in its large-scale structure, a collection of isolated islands, each local group of galaxies drifting through the dark on its own, out of contact with all the others, carrying forward whatever remains of its own stellar population with no reference to the wider cosmos. Within those isolated islands, the galaxies themselves will have merged. The Milky Way and Andromeda, already approaching each other at considerable speed, will have completed their collision and merger billions of years from now, forming a single large elliptical galaxy that astronomers sometimes call Milkomeda in anticipation. The stars within it will not collide. The distances between stars are so vast that even in a galactic merger, individual stellar collisions are rare. But the galaxies will lose their spiral structure, their distinct identities, and become a single, slowly rotating collection of stars, gradually aging together. And in that merged galaxy, across trillions of years, the remaining stars will quietly conclude their lives. The more massive ones first, then the smaller ones, then smaller still, until only the dimmest and most patient red dwarfs remain separated by distances that once contained the brilliance of entire stellar populations. What the universe feels like in that era, if feeling is a concept that still applies, is something researchers can describe structurally but not experientially. There are no analogies that map cleanly onto it. The closest the mind can reach is perhaps a very large room, growing very slowly darker, the light sources going out one by one with such long intervals between each one that the darkness accumulates without any single noticeable moment of change. Not a switch being thrown, just a gradual, patient dimming, extending across time scales that have no human equivalent. The period that follows after the last star has exhausted its hydrogen and faded is what physicists call the degenerate era. It is named for the type of matter that remains white dwarfs and neutron stars, objects supported by quantum mechanical degeneracy pressure rather than the heat of ongoing fusion. These objects do not burn. They do not produce new light. They simply persist, cooling in the dark, radiating their stored heat outward in a process so slow that the temperature drop across any span of time a human could meaningfully consider would be essentially unmeasurable. The degenerate era is estimated to last from roughly 10 to the 37th power years to perhaps 10 to the 45th power years, numbers that have left ordinary arithmetic so far behind that they function more as symbols of duration than as quantities. During this time, the remnants of stars will continue to cool. Occasionally, two white dwarfs will drift close enough to merge, releasing energy in a brief pulse of light before settling back into darkness. Neutron stars, still spinning, but slowing with every passing millennium, will gradually wind down. The universe will become quieter, darker, colder, not suddenly, but so gradually that the change accumulates across durations that no measurement system anchored in human experience can adequately represent. And yet the matter will still be there. The atoms that were forged in stellar interiors, the iron, the carbon, the oxygen will persist. They will not disappear. In the cold and dark of the degenerate era, they will drift in arrangements that no longer sustain life, no longer sustain light, but still exist in the full physical sense. The universe will not be empty. It will simply be very cold and very dark and very still. There is a quality to deep stillness that is not the same as absence. The mind, in its deepest sleep, goes somewhere that waking consciousness cannot follow and cannot later describe with any precision. Researchers who study the phenomenology of deep slow-wave sleep, the deepest stage, the one furthest from waking, the one in which the brain produces its slowest and most synchronized electrical oscillations, have found that subjective experience during this phase is minimal in the way that outer space is minimal. Not nothing exactly, but close enough to nothing that the distinction barely matters from the inside. People woken from deep sleep often report no sense of time having passed. No dreams, no narrative, just a gap, and then waking. And yet the biology during that phase is among the most active and restorative of the entire sleep cycle. The body is most deeply engaged in repair precisely when the conscious mind has gone furthest away. The stillness of experience does not reflect the stillness of process. The quiet is productive. The dark is doing something. Perhaps the degenerate era is in some abstract structural sense the universe's version of this. Not a dead phase, not a meaningless waiting room, but a long period in which the dramatic visible activity has ceased while the underlying processes, slow quiet, below any ordinary threshold of observation, continue. The universe persisting, holding its matter together, not going anywhere, not finished with whatever it is across incomprehensible timescales in the process of becoming. There are physicists who have speculated about what, if anything, might be possible in the deep future of the universe, whether structures of sufficient complexity could persist in the degenerate era, whether the slow release of energy from cooling white dwarfs could in principle sustain processes of sufficient subtlety to be meaningful, in some sense, not yet defined. These are not mainstream scientific claims. They are the careful provisional speculations of people who take the question seriously enough to follow it wherever it leads. They arrive at no firm conclusions. The question remains open in the way that questions about very long timescales tend to remain open, not because researchers have not thought carefully, but because the scales involved place the answers beyond any current means of verification. What is not speculative is the structure, the timeline, the sequence of cooling and darkening, the long patience of matter waiting in the cold. These are the conclusions of careful physics following established principles forward across extraordinary durations. And what they describe is not terrifying if you approach it with the right frame. It is, if anything, a kind of peace. The universe, having burned through its stellar age, having made everything it knows how to make, having distributed the products of that making across all the space it contains, settling, resting, becoming quiet in a way that it has never quite been quiet before. There is a breathing exercise that sleep researchers and practitioners of various meditative traditions have converged on independently across cultures and centuries for the simple reason that it works a slow, deliberate extension of the exhale beyond the inhale, allowing the nervous system to register the exhale's longer duration as a signal that it is safe to release. The inhale activates, the exhale settles, and when the exhale is allowed to be very long, longer than feels immediately natural, the system beneath the system, the one that decides how alert to be, how ready, how tense, begins to believe that the situation does not require its full attention. It begins to let go. The universe is in a very long exhale. Everything that has been built, everything that has been lit, everything that has burned and fused and scattered and reformed, all of it is gradually across a duration that exceeds imagination, moving toward a quieter arrangement, not toward nothing, toward stillness, the kind of stillness that is on the other side of everything having been done. And in a small room, somewhere, on a small planet, still within the stellar age of the universe, still within the era of light, still surrounded by stars, burning in their main sequences, still held in the warmth of a sun that has billions of years ahead of it, something is breathing. Slowly. The exhale a little longer than the inhale. The body settling into what comes after the effort. The darkness is not empty. It is full of everything that is resting. And just beyond, where this thought is dissolving at the very soft edge of what is still conscious and what is already something else, the next thing is already waiting, even quieter than this. Even after the last star goes quiet, the universe is not finished. That might be the most unexpected thing about the deep future, the part that resists the imagination most stubbornly, because the intuition says that darkness means ending, that when the lights go out, the story stops. But physics, which has a habit of being indifferent to intuition, says otherwise. In the era that follows the degenerate age, when white dwarfs have cooled beyond any meaningful glow, when neutron stars have spun down to silence, when the last organized warmth has dispersed into the surrounding cold, something is still happening. Not quickly, not in any way that resembles the dynamic luminous activity of the stellar age, but happening nonetheless in the slow and patient way that the universe tends to operate when it has all the time that remains. Black holes will still be there. Not numerous, not distributed evenly, but present the remnants of the most massive stars, the accumulated mass at the centers of galaxies, patient objects that have been slowly growing across billions and trillions of years by absorbing whatever drifted within their gravitational reach. Black holes do not radiate light through any conventional process. They do not burn or fuse or release energy through the means that made the stellar age luminous. But they are not, as it turns out, perfectly inert. In the 1970s, the physicist Stephen Hawking arrived at a theoretical result that surprised almost everyone who encountered it, including himself. Working at the intersection of quantum mechanics and general relativity, two frameworks that do not normally cooperate well, he found that black holes should in theory emit a very faint radiation. Not from inside the event horizon where nothing can escape, but from the boundary region just outside it, where quantum effects allow for the spontaneous creation of particle pairs. Occasionally, one particle of such a pair falls inward while the other escapes outward. The escaping particle carries energy away from the black hole. And over time, an incomprehensibly long time, this process causes the black hole to lose mass and eventually to evaporate entirely. Researchers call this Hawking radiation, and the timescales involved are so extreme that the phrase incomprehensibly long is being used with full seriousness. A black hole with the mass of the Sun would take approximately 2 × 10⁻�67 years to evaporate completely through this process. The supermassive black holes at the centers of large galaxies, objects with masses millions or billions of times that of the Sun, would take correspondingly longer. The largest known black holes might require something in the range of 10⁻100 years to fully evaporate. That number 10, followed by 100 zeros, exceeds even the timescales of the degenerate era by such an enormous margin that the entire previous history of the universe, all 100 trillion years of the stellar age, would represent an almost negligible opening fraction of the time remaining. And yet across that duration, each black hole will quietly radiate, will lose particle by particle the mass it accumulated over its entire existence, will eventually, in a final brief pulse of energy, cease to exist entirely. Physicists sometimes describe the final moments of a black hole's evaporation as a burst, a last release of energy as the remaining mass drops below a critical threshold and the Hawking radiation accelerates. But burst here is relative. Even this finale is by any standard except the cold mathematics of quantum field theory an incredibly minor event. A flickering, something that would be imperceptible across astronomical distances without instruments of extraordinary sensitivity. And then nothing, just the diffuse, almost featureless bath of thermal radiation that the evaporated mass has become distributed across space so thinly that it barely distinguishes itself from the background. After the last black hole evaporates, the universe will enter what physicists have called the dark era, a phase in which no structures of any significance remain. The matter that was once organized into stars and planets and dust clouds will have been redistributed through various decay processes into its most stable elementary forms, primarily photons, electrons, positrons, and neutrinos, all drifting through an expanding universe at temperatures approaching absolute zero. Not absolute zero, which is a limit that cannot technically be reached, but close, extraordinarily close, a universe almost indistinguishable from perfect stillness. Whether anything further happens after that point is a question physics cannot currently answer with confidence. Some theoretical frameworks suggest that even the protons making up ordinary matter may eventually decay over timescales measured in 10 to the power of 33 to 10 to the power of 40 years. The protons that form the nuclei of atoms may spontaneously transform into lighter particles, releasing tiny amounts of energy in the process. If proton decay occurs, then even the cold remnants drifting through the dark era will eventually dissolve, and the universe will become, over timescales truly beyond any frame of reference, a thin and featureless gas of elementary particles, growing colder and more diffuse without limit. If proton decay does not occur, and experiments have so far not confirmed that it does, then the cold remnants may persist much longer, and the story continues in ways that current physics cannot clearly trace. Both possibilities arrive at the same general destination, a universe that is quieter than anything currently conceivable. Not empty in the technical sense, but effectively featureless, expanding, cold, patient, beyond measure. There is a particular quality to this picture that is easy to mistake for bleakness, but which, held quietly and without agenda, feels more like something else, something closer to completion. The sense of a process that has run its full course, not cut short, not interrupted, but allowed to proceed without interference to wherever its own internal logic leads. The human brain has a complicated relationship with open-endedness. Researchers who study what happens cognitively when a narrative lacks resolution have found that incomplete stories tend to create a low-level cognitive activation, a background processing that continues even when the conscious mind has moved on, as the brain quietly works to supply the missing ending. Psychologists sometimes call this the Zeigarnik effect, after the early researcher who noticed that people tend to remember incomplete tasks better than completed ones, precisely because the brain keeps some portion of its attention on unfinished things. But completion produces something different. A genuinely resolved situation, one in which the process has reached its natural conclusion, allows the brain to release the processing it was maintaining. There is a kind of cognitive exhale that comes with actual endings, distinct from the relief of avoidance or the numbness of shutdown. It is the specific relaxation of no longer needing to hold something in anticipation. Sleep researchers have found that one of the things that disrupts the transition into rest most reliably is the presence of unresolved mental loops, thoughts, or concerns that the brain keeps returning to because they lack resolution. The mind stays partially alert as long as it believes there is something that still needs attending to. And one of the things that most helps the transition is the quiet, deliberate practice of setting things down, not solving them, not resolving them artificially, but consciously releasing the obligation to continue holding them, acknowledging that they can exist without being actively maintained, that the night does not require their resolution that they will still be there, unchanged, whenever they are needed again. The universe, in its long arc toward the Dark Era, is doing something structurally similar. It is across timescales no biology will ever witness, completing its open loops. The black holes evaporating, the remnant matter decaying, the energy redistributing into its most diffuse and stable form. Each process running to its conclusion, not because anything is forcing it, but because the physics that governs it is simply following the logic of what it is, until there is nothing left to resolve. There is no urgency in it. That is perhaps the most important thing to notice. The universe is not rushing toward the Dark Era. It is not trying to arrive there. It is simply proceeding at the pace determined by the physics of Hawking radiation and proton decay and the slow expansion of space, doing what it does step by step across durations that make every other span of time feel trivial. And somewhere in the very early moments of that arc, incomprehensibly early by the standards of what is coming, a living thing on a small planet is lying in the dark, and its brain is doing something that the universe, in its way, is also doing. Processing, completing, releasing the threads that no longer need to be held, allowing the unresolved things to remain unresolved for a while, not because they do not matter, but because the night does not require their resolution. The body knows this even when the mind resists it. The body has always known when to stop. There is a state that researchers describe in the transition between light sleep and deeper sleep, a brief hypnagogic window in which the visual and auditory systems, no longer receiving meaningful input from the environment, begin to generate their own. Images without source, sounds without origin. The mind produces in that in-between space fragments of experience that belong to no waking moment faces, landscapes, voices, movements, all drawn from the residue of everything the day contained and assembled into something that is not quite dreaming and not quite thought. Scientists are still exploring exactly what this state represents and what function it serves. There are suggestions that it may be a kind of processing mode, a transitional state in which the brain loosens its normal categorical structures and allows material to be recombined more freely before the deeper organizational work of full sleep takes over. It may be a clearing, a sorting, a brief moment of creative disorder before the system settles into its more structured repair cycles. It is in any case one of the stranger gifts the brain offers, this brief window where the ordinary boundaries between inner and outer, between memory and perception, between now and then, become genuinely soft. And if you are in or near that window now, if the images are beginning to come untethered from their explanations, if the thread of this is growing loose and easy to hold, then something is already working. Something is already doing what it is supposed to do. The universe in the dark is not waiting for something to happen. It is the happening. It is the slow, patient, unwitnessed continuation of everything that has already been set in motion. Hawking radiation crossing incomprehensible spans of time. Particle pairs emerging at event horizons. Black holes losing their mass, gram by gram, across durations that dwarf the entire stellar age. All of it proceeding, all of it moving in its own direction, without haste, without audience, without any need for observation to make it real. And just here, in this particular small dark, in whatever room or bed or quiet corner, this night finds you something is also proceeding, also moving in its own direction, also doing what it does without being watched. The thoughts are softer now, if there are thoughts. The distance between them a little longer than before. And in the next silence, something even quieter is waiting, the part of the story where the universe and the mind, listening to it, arrive at the same place, at the same time, from very different directions, by very different roads. There is a question that emerges almost inevitably somewhere along a journey like this one. Not a loud question, not one that demands an answer or creates urgency. More the kind of question that arrives quietly, somewhere between one thought and the next, the way certain questions do when the mind has grown soft enough to hold them without immediately reaching for resolution. The question is something like, does any of it matter? Not asked with despair, not asked as a challenge, but genuinely openly in the way that a person lying still in the dark sometimes allows themselves to wonder about things they would not pause long enough to consider during the day. If the universe tends toward cold and dark, if the stars go out, if every structure eventually dissolves into featureless equilibrium, then what is the weight of a moment? What is the weight of a life? Physics, interestingly, has something to say about this, not as an answer, but as a reframing. The second law of thermodynamics is one of the most fundamental and most tested principles in all of science. It states in its simplest form that the total entropy of an isolated system always increases over time. Entropy in this context is a measure of disorder, or more precisely, a measure of how many possible arrangements a system's components could take while still producing the same observable result. A highly ordered system has low entropy. A highly disordered one has high entropy. And the second law says that left to itself, disorder tends to increase. Things spread out. Energy distributes. Organized structures give way to more diffuse ones. The universe overall moves in the direction of greater and greater entropy. This is why heat flows from hot to cold, and not the reverse. Why a drop of ink disperses through water, but never spontaneously reassembles. Why the ordered fuel of a star eventually becomes the diffuse radiation of its aftermath. The arrow of time, the fact that processes run in one direction and not the other, that cause precedes effect, that the past is fixed and the future is open, is intimately connected in the physics to the direction of increasing entropy. Researchers who study the statistical mechanics underlying thermodynamics describe entropy not as a force, but as a probability. A highly ordered state is simply far less probable than a disordered one. There are combinatorially vastly more ways for a system to be disordered than ordered. And so, over time, systems tend to drift toward the more probable arrangements, not because anything is pushing them there, but simply because there are more ways to be disordered than organized, and random processes sample the available possibilities without preference. What this means for the deep future of the universe is that the long arc toward the dark era, the cooling, the dispersal, the dissolution of organized structures, is not a tragedy in the thermodynamic sense. It is simply the universe exploring the space of its possibilities, drifting as all things drift toward the more probable arrangements. The stellar age, with all its complexity and light and improbable chemistry, was the universe in a state of extraordinary temporary, hard-won low entropy. The stars themselves were pockets of organization maintained against the general tendency sustained, as everything organized must be, by the expenditure of energy. Life is perhaps the most striking example of this. Living systems are by any thermodynamic measure highly improbable structures. They maintain themselves at a state of very low entropy complex, organized information dense, by continuously consuming energy and expelling waste heat. A living cell is not violating the second law. It is complying with it at a local level by using the flow of energy through it to maintain its organization at the cost of increasing disorder in its surroundings. Life persists, not despite the tendency toward entropy, but by working with it, channeling it, directing it, finding the narrow pathways through which order can be locally sustained. The physicist Erwin Schrödinger, writing in the 1940s, described life as something that feeds on negative entropy, meaning that it sustains itself by drawing in ordered low-entropy energy and releasing higher entropy waste. The flame of a candle, the metabolism of a cell, the cognition of a brain. All of these are local temporary structures that maintain their organization by participating in the broader flow of energy from concentrated to diffuse. The brain specifically is one of the most energetically expensive organs in the known universe relative to its size. It consumes in a resting human somewhere around 20% of the body's total energy budget, despite representing only about 2% of body weight. This is an extraordinary investment for a biological system to make in a single organ. And researchers who study neural energy consumption have found that much of this energy goes not toward any specific computation or task, but toward maintaining the baseline readiness of the neural network, keeping the billions of neurons and their trillions of connections in a state of low entropy, ready to respond, available to process. The resting brain is not idle. It is expensive to maintain. The default mode network, a set of brain regions consistently active during rest and quiet reflection, consumes nearly as much energy as the brain uses during demanding cognitive tasks. Researchers have found that this network is involved in mental simulation, in imaginative projection, in the integration of autobiographical memory with the present moment. It is, in a sense, the brain sustaining its own internal model of the world and the self, a continuous, energetically costly act of keeping that model coherent and available. Sleep reduces the energy cost of this maintenance. During sleep, certain aspects of the default mode network quiet. Certain connections loosen. The brain's continuous self-modeling relaxes its grip, allowing the system to perform maintenance that the expensive state of waking readiness prevents. And when this happens, when the high-energy state of waking cognition gives way to the lower-energy state of sleep, something is gained, not lost. The maintenance that could not happen while the system was alert can now proceed. The repair cycles that waking suppresses can run. The universe, in moving toward higher entropy, is doing something that rhymes with this, releasing the energy expenditure required to maintain its organized structures, allowing the improbable configurations of the stellar age to relax into more probable ones. And in doing so, as with sleep, it is not destroying what existed. It is releasing the cost of maintaining what existed in its concentrated form and redistributing the proceeds across a wider space. The question of meaning, then asked softly in the dark without agenda, might be less about whether organized structures persist forever and more about what it means that they existed at all. There is a physicist's way of thinking about this and a more personal one, and they are not incompatible. The physicist's version involves something called the anthropic principle. In its most minimal form, the observation that for any observer to exist and ask questions about the universe must already have been in some region and for some duration, the kind of place that permits observers to exist. The very fact that something is lying here, wondering about the long-term fate of the cosmos, is evidence that the cosmos has at least locally and at least temporarily sustained the conditions for wondering. It is a tautology, but a strangely useful one. The universe did not have to produce conditions for complexity. That it did here, in this stellar age, on this planet, with this chemistry, is not guaranteed by the laws of physics alone. It required a particular history of low entropy expenditure, an extraordinarily specific sequence of events. The more personal version simply notices that this is now, not the dark era, not the degenerate age. This, whatever particular configuration of atoms and energy and experience, is occurring in this moment, in this body, in this quiet. It is happening during the era when the universe is still lit, still making stars, even if more slowly, still holding the conditions for complexity, for warmth, for the kind of organization that can wonder about its own existence. There is a concept in positive psychology and contemplative neuroscience that researchers have studied under various names: presence temporal grounding, the here and now orientation, which describes the cognitive state of being genuinely located in the present moment, rather than running simulations of the past or future. Studies have consistently found that people report higher subjective well-being when their minds are present in the current moment than when they are elsewhere, regardless of whether the task they are performing is pleasant or neutral. The wandering mind, the researchers note, is often an unhappy one, not because the future or past it visits is necessarily dark, but because the act of not being here carries its own low-level cost. And the particular quality of the present moment, when it is actually occupied, when the body is felt, the breath is noticed, the sounds of the room are registered, has a specificity to it that memory and anticipation do not. It is textured. It is immediate. It is, in the most literal sense, the only place where experience actually occurs. The universe, in all its vast and patient arc toward entropy, has produced here and now a moment of experience, a mind turning thoughts over in the quiet, a body warm and resting, a night doing what nights do. That is not nothing. That is, by any thermodynamic accounting, an extraordinarily improbable arrangement, one that required billions of years of stellar evolution, dozens of stellar generations. The specific history of this planet, the specific sequence of biological development, the specific day that preceded this specific night, all of it converging on this exact configuration of matter and energy and awareness. The universe has no opinion about whether this is meaningful. It does not have opinions, but it did somehow produce it. And what the mind does with that, how it holds it, what it feels like, to let it simply be there without requiring it to mean something specific or be explained or be resolved, that is not a scientific question. That is something closer to what happens in the space between questions. The open, unheld thing. The breath that does not need a reason. Researchers who study the psychology of awe, the specific emotion triggered by encounters with vastness, complexity, or phenomena that exceed ordinary frameworks of understanding, have found something consistent and somewhat counterintuitive. Awe tends to reduce the subjective sense of time pressure. People experiencing awe report feeling less hurried, less behind, less in need of any particular thing to happen next. The vast thing encountered, whether a mountain range, a night sky, a piece of music of unexpected depth, seems to expand the present rather than diminish it. The self feels smaller in one dimension and larger in another. Less urgent somehow, but not less real. The neuroscience of this is still being mapped, but the functional observation is well replicated. Vastness quiets the noise of the urgent self. It does not make the self disappear. It simply places it in a context large enough that its habitual anxieties lose their proportionate weight. And this perhaps is one of the oldest things the night sky has ever done for anyone who has really looked at it. Not provided answers, not resolved the question of meaning, but offered something that questions themselves cannot provide a context large enough that the need to resolve them, at least for a night, at least in this hour, gently releases its grip. The universe tends toward entropy, and somewhere in that long, patient tendency, somewhere in the extraordinary local exception that is a life, a night, an awareness, quietly turning these thoughts over in the dark, the question of meaning is already somehow less urgent than it was a little while ago. Not answered, just held differently, more loosely, with the hands a little more open than before. And just beyond this, very close now, at the soft edge of where the story and the silence begin to become the same thing, the last light is waiting. Not with any urgency, just there, the way endings that have been approached gently tend to be there, quietly, already part of the night. The last star will not know it is the last. That is the first thing worth sitting with here, at the end of everything this night has been moving toward. Not as a sad thought, not as anything that requires a response, just as a fact that has a particular texture to it, the way certain true things do when you hold them in the quiet. A star has no awareness of the other stars, no sense of its place in the larger population, no knowledge of the eras preceding it, no understanding that the universe it inhabits was once full of light at a density it will never know. It simply burns. It does what its mass and its chemistry and its position in the galaxy determine that it will do. It fuses. It balances. It holds. And the last one will do exactly that, will go through its complete life, however many trillions of years that life extends, without any knowledge of the significance attached to it from whatever vantage point could observe it. It will be to itself simply a star among stars. The fact of its being the final one is a property of the whole, of the entire history of the universe, and not of the star itself. Scientists describe this kind of property as emergent, a quality that belongs to the system, not to any individual part of it. The last star is not different from any other red dwarf. It is the last only in relation to everything that came before it, everything that surrounded it, and preceded it, and will not come after. Its meaning, if meaning is the right word, is relational, held in the space between itself and everything else. The universe has produced many things that are like this, properties that only exist in the context of relation. Color, for instance, is not a property of objects themselves. It is what happens when a particular wavelength of light interacts with the specific photoreceptors of a specific kind of eye. The redness of something is not inside the thing. It arises in the encounter between the thing and the perceiver. Remove either one, and the redness does not exist. Researchers in perceptual psychology have spent decades documenting just how much of what feels like objective reality is in fact a product of the relationship between the sensing system and the world it senses. The warmth you feel is not simply a property of the air around you, it is the product of thermoreceptors in your skin, registering a temperature differential, and your nervous system interpreting that signal in a way that has been calibrated by a lifetime of thermal experience. Two people in the same room can experience different temperatures from the same air. The sensation belongs to neither the air nor the person alone. It belongs to the interaction. The brain, researchers have found, is not a passive receiver of a pre-formed world. It is an active constructor of experience, constantly generating predictions about what is out there and updating those predictions as incoming sensory data either confirms or corrects them. What you perceive is, in a very precise scientific sense, a model, a best current estimate of what is real, generated by the most energetically expensive organ in the body, running on billions of years of evolutionary refinement. The world you experience is not the world as it is. It is the world as your nervous system has learned over the course of a lifetime to expect it to be. This is not a diminishment of experience. It is in some ways its elevation, because it means that every moment of perception, every color seen, every sound heard, every sensation of warmth or texture or weight is an act of creation as much as reception. The mind meeting the world, and in that meeting producing something that neither contains alone. And in sleep, that meeting pauses. The sensory channels quiet. The predictions stop being updated with new incoming data. The model the brain has been maintaining of the external world loses its moment-to-moment grounding and begins in the deeper stages of sleep to disengage from the external entirely. What remains is the interior, the biological rhythms, the repair cycles, the memory consolidation, the dreaming, a period in which the brain turns at least partially away from the world outside and toward the world inside. Researchers have described this as a kind of daily dissolution and reconstruction. Every night, the model of the self and the world softens its boundaries. The tight coherence of waking identity, the sense of being a particular person in a particular place at a particular time, loosens, and in that loosening, something is processed that cannot be processed in the constrained state of waking attention. By morning, the reconstruction has occurred. The model is updated, refreshed, returned to coherence. But it is not quite the same model it was the night before. Something has been integrated. Something has shifted quietly in the night. The last star cooling in the dark is doing something that has its own gentle resonance with this. As it fades over millions of years from its full main sequence, brightness, through the expanding phase of its late life, and finally into the quiet, white dwarf cooling that will occupy its longest chapter. It is not simply ending, it is redistributing. The light it emits, the heat it radiates, the material it sheds across the long arc of its existence, all of it is moving into the space around it, being absorbed, being carried, becoming part of the thermal background of an aging universe. Nothing is lost in the thermodynamic accounting. Energy is conserved. The material of the last star does not disappear when it fades. It disperses. It becomes part of the fabric of whatever the universe is in that distant era, part of the diffuse cold, extraordinarily thin medium of particles and radiation that fills the space between the last remnants. The light of the last star will travel outward after the star itself has gone dark. Photons released in its final years will continue across a universe that no longer contains a living star, crossing distances in silence, moving at the only speed they know, carrying the last warmth of the last fire into the permanent dark, and eventually in a universe that has cooled so thoroughly that the distinction between light and background is measured in fractions of a degree above absolute zero. Even those final photons will have lost almost all their energy, redshifted by the expansion of space into wavelengths so long they barely constitute radiation in any meaningful sense. Not gone, just quieted to the threshold of nothing. And the universe, at last, will be very still. Not empty. Still. There is a difference, and it matters. Stillness is not the same as absence. Stillness is what remains after all the motion has found its level, after the currents have run their course, after the oscillations have damped to something below the threshold of any instrument. Stillness is the universe no longer requiring anything of itself, not burning, not building, not organizing, not dissolving, just existing in the most minimal and most complete sense of that word. There is a moment in some nights, not every night, but some, when the body reaches something like this. Not unconsciousness, something more subtle than unconsciousness. A state in which the breathing is so slow and so even that it seems to have always been this way, in which the weight of the body against what it rests on has become simply part of the geometry of the room, in which the thoughts, if any remain, have the quality of things very far away, visible, in outline perhaps, but not touching anything. Researchers who study the subjective texture of sleep onset describe moments during the hypnagogic state in which people report a sense of expansion of the self, becoming less bounded, of the room extending beyond its walls, of time losing its forward pull. Not a dramatic sensation, more like something that is noticed only in retrospect, if at all. The edges of things becoming soft. This is not sleep yet, but it is near it. It is the body discovering, as it does every night, that it knows what to do when given the chance. That beneath the constant activity of waking, beneath the decisions and the reactions and the low-level maintenance of alertness, there is something that has been waiting for exactly this. Something that does not need instruction or preparation. Something that simply given stillness and darkness and the quiet that has gathered over the hours of this night begins to open. The last star burns in its long and patient way, alone in the vast dark, without knowledge of its singularity, and somewhere at a distance that the light from that star will never cross, in a time so far removed that even the mathematics struggles to hold it, something that was once made of earlier stars' ash is resting, is quiet, has followed a story all the way to its soft and open ending, and is now perhaps somewhere between the story and what comes after, which is not nothing, which is the oldest and most ordinary gift the universe offers, the chance to stop and let the dark be what it is, and trust that by morning the reconstruction will have happened quietly without any effort on your part. You don't have to do anything with what tonight has carried. It will find its own place the way things do in the dark. The breath moves slowly, and the space between one breath and the next is already longer than it was. And in that space, in the particular silence, this night has built layer by layer, from the first star to the last. There is nothing left to hold. Only this, only rest.